In this chapter, we will look at a comparison of two wheels that have identical total masses but different moments of inertia, and we will compare the rates of angular acceleration and deceleration, and then look at some conclusions.
Some facts are not left to debate, like theories that some fabricate. There's no disputing the physics of Newton. Just watch as I demonstrate. People sometimes make all kinds of statements about wheels, and I find that some of them simply cannot be true, because at the end of the day, there's this truism: wheels have to live with the laws of physics. In this chapter, I'll show you a nice demonstration that clarifies and provides a good example of what I mean.
These are two wheels that we'll use for an experiment. The wheels are identical except for one thing. The wheel on the left has a chain wrapped around the circumference of the rim, and the wheel on the right has a chain of the same length wrapped around the hub. If that's hard for you to visualize, here's the chain and the wheel. Here's the chain laid out lengthwise, and here it is wrapped around the circumference of the wheel. Here's the other wheel with the chain laid out, but instead of wrapping the chain around the rim, we're going to wrap it around the hub. So here is one wrap, then we wrap it again, wind another section on, and another section on, and so on, until we end up with this, where all of the chains has been wrapped around the hub. Let's make a little table here showing the component, its description, and its mass in grams. The note here says that the masses were empirically determined with a metric balance, so they should be accurate. First, we have a rim. The rim is a Stans Alpha 340 rim. Note 2 says that this is the original version of the rim with the lightest mass of 360 grams. Then we have a hub, a Velocity Road hub, 414 grams. We have spokes, 32 altogether, DT Swiss competition, 16 of which are 288 millimeters long, 101 grams, and 16 more that are 290 millimeters long, 103 grams. Nipples, alloy nipples, 32 of those, that's 10 grams. And then I have a chain. The chain is a KMC chain, a 1/8 inch chain, and if we look at note 3 here, we see that I had to use 138 links to go all the way around the circumference. So I needed to add 2 lengths of chain together. I actually have 1.23 lengths of chain in each wheel, and that is another 493 grams. I then calculated the moment of inertia of each component. The wheel on the left has the chain on the rim, and the wheel on the right has the chain on the hub. In most cases, I get the same values. I get the same moment of inertia for the rim, for the hub, for the spokes, for the nipples, but the chain, of course, is different depending on its location in reference to the radius and the center of the wheel. If we arithmetically add those columns, we see the total moments of inertia shown at the bottom. The results show us that for each wheel we have a total mass of 1,481 grams, but showing the figures on the right under the totals converted to the number of significant figures we're entitled to, we have 0.0871 kilogram meter squared where the chain is on the rim, and 0.0392 kilogram meter squared where the chain is on the hub. Here we see both wheels mounted for an experiment. This is the wheel that has the chain wrapped around the rim. Here the chain is around the hub. We have 500 gram weights ready to fall and accelerate each rim. These are instrumented with magnets, with sensors, and with computers to record velocity. These particular computers only read in miles per hour, but that of course is easy to convert back to meters per second. Here's a picture of one wheel has been mounted for the experiment. We can see in this case that the chain is wrapped around the circumference of the rim. The wheel is attached using a bracket to a steel beam, and the wheel is all held in place to the bracket with a skewer. Here's a close-up where we can see some fishing line wrapped around many times around the free hub body and attached at the other end to a weight. Here is the other wheel, and once again you can see in the bottom picture the fishing line wrapped around the free hub body. The free hub body, of course, is where the gears normally go, so that when you turn the gears clockwise, the wheel turns. In this case, I'm using the weights and the fishing line that's wrapped around the free hub body, and as the weights fall, that will make the free hub body likewise turn clockwise and make the wheel spin. We're all set up with the wheels mounted. There's the floor. There is potential energy in each weight, which is equal to its mass of 500 grams, times the force of gravity, which is 9.81 meters per second squared, times the height of the weight in reference to the floor, which is 2.08 meters. That is the distance, of course, that the weight will drop. And as it does, starting out with a potential energy in the weight of 0.500 kilograms times 9.81 meters per second squared times 2.08 meters, that will give me a potential energy in each weight of 10.2 kilogram meters squared per second squared, and that is 10.2 joules. As the weight falls and hits the ground, all of that potential energy that was in the weight will be converted to kinetic energy of rotation of the wheels. At the same time that the weights hit the floor, the fishing line that's attached to the hubs will be released and the wheels will spin freely. Each wheel will find itself with a kinetic energy of rotation of 10.2 joules. The kinetic energy in each case will be equal to 1/2 the moment of inertia of the wheel times the angular velocity squared. I already know what that is, and I have calculated the moment of inertia already, but I have to figure out what omega is. I can rearrange this equation, plug in the numbers I have, and solve that. And when I do, I'll find that omega is equal to the square root of the kinetic energy of rotation divided by 1/2 I. And plugging in the numbers I already have, I end up with this square root here. Multiplying out the numerator, I get this expression here that the angular velocity is equal to the square root of 20.4 joules divided by the moment of inertia. We already know what I is. These are the values for I that I calculated a couple minutes ago. Here I plugged in the respective moments of inertia for each wheel, and that gives me a predicted maximum rotational velocity of 15.3 radians per second for the wheel on the left and 22.8 radians per second for the wheel on the right. I just moved those two calculations out to the side so I can show you in the space in the middle how it is that I know that the units worked out as shown. So we'll take this expression here and move it up there. Getting rid of the numbers and just showing the units, I get this. Substituting kilogram meter squared per second squared for joule. Doing some canceling. Leaves me with this, and when I take the square root, and then I can show my angular velocity this way, or I can show it as radians per second to help me keep track of radians if I want to do that. In each case, we want to convert this rotational velocity in radians per second 2 revolutions per second, and we start with this, that 1 revolution is 2 pi radians, which is 6.28 radians. On the left, we start with omega being 15.3 radians per second, and we're going to multiply that by 1 revolution per 6.28 radians. Radians cancel out, and we get omega equal to 2.44 revolutions per second. On the right, we start with omega being 22.8 radians per second. Multiply that by the same conversion. Radians cancel out again, and we get omega being 3.63 revolutions per second. This, by the way, is a good example of the benefits of dimensional analysis. Using the example on the left and a quick illustration I'll show you what I mean. We start with 15.3 radians per second, and we have to multiply that by some conversion factor to get our answer in revolutions per second. I know that 1 revolution equals 6.28 radians, so from that I can write 2 expressions. 1 revolution divided by 6.28 radians equals 1, or the other way around, 6.28 radians divided by 1 revolution also equals 1. So how do I know which of those 2 conversion factors to plug into those parentheses? If I use the one on the left, I see this. Radians cancel out, and I get my units as I want in revolutions per second. If I use this conversion factor, I'm going to get radians squared in the numerator, and in the denominator, seconds revolutions, and that obviously is not what I want. So by letting my units guide me, I use the correct conversion factor. My outside radius right to the edge of the rim is 315 millimeters. My circumference is 2 pi times the radius, which is 2 times 3.14 times 0.315 meters, and that gives me a circumference of 1.98 meters for each wheel. Now I can determine my calculated linear velocity of the rolling wheels, because if I multiply in each case the revolutions per second times the meters per revolution, then I will get my revolutions canceling out, and that will give me results in terms of meters per second. And I can convert meters per second easily into miles per hour. So my calculations tell me that my maximum linear velocity of the rolling wheel should be 10.8 miles per hour for the wheel where the chain is on the rim, and 16.1 miles per hour for the wheel where the chain is wrapped around the hub.
Having set the stage, let's let the weights drop and see what happens to the wheels.
Here we have both of these wheels set up side by side, and we're going to release them both at exactly the same time and then watch as the 2 weights drop. What we've obviously seen here is that the wheel on the right that has the chain around the hub, the weight dropped rather quickly. The wheel spun up fast, but the wheel also slowed down rather quickly.
the wheel on the left, the weight was slower to drop. The wheel was slower to spin up, but continued spinning a longer period of time. We're going to do the same thing again from a closer viewpoint, and you'll see little windows appear that will show the bicycle computer so we can actually see what the recorded velocities are.
You'll hear me mention a few elapsed times that I'm recording with the stopwatch. 13.0 is when the weight hits the ground. Okay. 22.3 seconds.
You're not timing how long it spins for?
I already did that. This here, I had to redo this because I forgot to turn the light on before when I filmed this one, and the computer, this computer doesn't have a light on it, so it doesn't show up too well without an external light. All right, so this is an experiment that was done in a two-dimensional system, meaning that all movements are in one plane. And that gives us a constant vertical acceleration of the weight of 9.81 meters per second squared. That in turn gives us a constant angular acceleration of the wheel of radians per second squared. And that in turn gives us a constant linear acceleration of the wheel in miles per hour per second. In that last term, second is not squared because the numerator already has a time element in hours.
And just for the fun of it, we can plot some graphs and see what our data looks like.
We can plot linear acceleration on this graph. On the x-axis is time in seconds. On the left y-axis is velocity in miles per hour, and on the right y-axis is in velocity in meters per second. We will be plotting our experimentally determined values. In the graph, the wheel with the chain around the hub that accelerates the fastest will be shown with green lines, and the wheel with the chain wrapped around the rim, which accelerates the slowest, will be with blue lines. The faster wheel in about 12.5 seconds hit a velocity of about 15 miles per hour. That gives us this line here and an acceleration on the average of 1.20 miles per hour per second. The other wheel took about 19.5 seconds to get to 10.5 miles per hour, and that gives us this line and an average acceleration of 0.54 miles per hour per second. And on this graph, we're going to plot linear acceleration again and deceleration, which is much slower, so we've extended the x-axis to 100 seconds, not just 20. These, on a different scale, are the same acceleration lines we saw a minute ago, but whereas the fast wheel slows to a stop after 47 seconds, the slower wheel continues to roll for 76 seconds. The wheel with the chain wrapped around the hub decelerates at the rate of 0.435 miles per hour per second. The wheel with the chain wrapped around the rim decelerates much more slowly at only 0.186 miles per hour per second. If we imagine the rollout distance for each wheel, theoretically, each wheel will roll to the same point and stop because the same amount of kinetic energy has been imparted to each wheel.
What you've seen is more of a demonstration than an experiment, but it's still interesting to look at what some of the sources are of experimental error.
So let's make a little table, a comparison of the calculated and empirical values of Vmax, the maximum velocity, linear velocity that the wheel achieved. Here we go, wheel, calculated Vmax, empirical Vmax and difference. Of course, we have the wheel with the chain on the rim and the chain on the hub. With the first one, we had a calculated Vmax of 10.8 miles per hour, empirically determined 10.5, difference of 0.3 miles per hour, which is about a 3% error. With the chain on the hub, calculated 16.1, empirically determined 15, difference of 1.1 miles per hour, which is about 7%. What might be some of the sources of experimental error? The first of these would be the force to overcome initial static friction. There's static friction and kinetic friction, and static friction can be considerable. There's also aerodynamic drag as the wheel spins faster, particularly in the spokes. These first two will be gone into in great depth in later chapters. Then there's stretching in the nylon fishing line, and that causes the weight to hit the ground sooner than we calculate. Then there's the sampling rate of the sensor and the computer, and with the computer you get really an average versus an instantaneous velocity, so the average velocity is always going to be a little bit less than the instantaneous velocity as the wheel is accelerating.
I think that was a pretty good demonstration to show you the relationship between angular velocity and the moment of inertia of a wheel.